Hello guys, thank you very much for the introduction. I'm glad to see great people who decided to attend my presentation on Sunday. Indeed, I will be talking about analyzing client-side JS for endpoint, PHP endpoint discovery. Now, let me briefly tell you who I am. So, name is Daniil Sigalov. I work for SolidSoft. I am also an associate at Moscow State University Computer Science Department, and I'm also a member of the Bushwhackers team. We do CTF. Now, at SolidSoft, we develop a black box scanner called SolidPoint. What I do for this team is a particular component, which is in fact the analyzer I will be talking about today. So, besides this being a component of the scanner, it's also what I'm doing my thesis on. Indeed, two years ago, I made my presentation about pretty much the same analyzer. If you haven't watched it, you can actually follow the link here. Even if I say so myself, I think it was a pretty useful presentation. And you don't really need to scan it right now. There will be another link at the end of my presentation. So let me briefly explain what it is that we're doing and why. Now, we want to increase coverage as we look for vulnerabilities. So it could be server functions or server APIs, whatever you call it. So we want our scanner, during the scan, to consider as many server endpoints as possible, because the more it looks for, the more vulnerabilities it can potentially find. So obviously, if you're doing, say, a manual pen test, you would also want to have something like this. Now, we are looking for the server handles, as I playfully call them here, on the client side, which is obviously one of the most natural ways of looking for server functions, as we're trying to invoke it from the client side. To be more precise, we are trying to check what kind of request can be sent from the client side to the server. As we're trying to determine that, the biggest difficulty is associated with the JavaScript code. So we send from HTML. It's not too difficult really to find these calls because we can do parsing of the HTML markup. With JavaScript, it's not that simple. Usually, in order for us to identify which specific calls are made, we will be using dynamic crawling. So dynamic crawling is automated interaction with the page elements, with the page interface. So effectively, the crawler will perform certain actions emulating user behavior. It will be, say, clicking different elements. It will be entering some text and will be sending forms and will scroll pages, in the hope that it is going to trigger a code execution that will send some request to the server. So if a request gets sent, it will see it in the traffic, and thus it will effectively discover it. So it's all about. I'm sorry, and the idea here is that triggering code execution is dynamic analysis, while we decided to apply static analysis. So you may be wondering what that is. So let me remind you briefly here what the content of my presentation 2 years ago was. So our JS analysis algorithm is like this. Our analyzer will be looking for calls in the JavaScript code, callbacks to the server and their arguments. Now, if we can find them and identify the arguments used there, well, then obviously we should be able to see what kind of calls these are. So these are for both, calls embedded in the browser, such as fetch and XML HTTP request, as well as the ones used to invoke popular libraries such as jQuery, Axios, AngularJS. Now, the calls in the code are usually easy to recognize by their name, so syntactically. So the analyzer simply knows that a function is invoked called $.ajax or HTTP post or a fetch. Well, it knows what that means. Now it runs above the AST abstract syntax tree, so it doesn't build CFG, and it spans the whole expanse of the page, and then it goes down the AST. It will also calculate value associated with a particular variable and will commit it to memory. And when it runs across an AJAX call, which obviously sends something into the server, the analyzer will calculate its arguments. So when I say AJAX call, I will be referring to pretty much any call from the JavaScript to the server. So it could be fetch or access, not just the AJAX itself. So besides assigning variables, the analyzer will also compute array variables and will use them going forward. The algorithm also supports the values that are supported by the standard system of JavaScript types, such as figures, strings, objects, arrays, and so on. It also supports two abstract values such as unknown and from arg. If the analyzer cannot calculate the value of a particular expression, then it will flag it as unknown. And it will simply store just a single value for each and every variable. It will also support a bunch of embedded operations in JavaScript, such as plus, reading fields, and so on and so forth. So in order to do its computation, it should be able to, access the fields where the individual elements are. It will ignore calls to user functions. So if it says something else in the code, it will simply assign a known to its result. It will also ignore the forking conditions, meaning that, branches of cycles and conditional operators will only be looked at once. The analyzer also contains a mechanism for searching for argument values. So if it needs to identify an argument for a given function, it will look for the areas where it's called and will analyze there to see what kind of arguments it comes with. However, this algorithm only works for freestanding functions, where effectively functions are treated as variables, which means that, if there is like a method being invoked or a callback, that is like a function which is used as a callback, which is used as an argument of another function, then it won't really apply. Now, what have been the difficulties we've run into? Now, JavaScript is difficult to analyze statically. This is an issue for any analyzer, not just ours, and just like any other static analyzer, we will be struggling with a dynamic code loading and eval, and code that was bundled with a bundling, or the code that would be using object-oriented programming, using classes or properties or methods, would be challenging as well. So I'm showing here two examples where we wouldn't be able to find much with our analyzer. So one is this, user-announced method, starting with this, and another one is a jQuery object which got renamed. So the analyzer here is identifying them by name. So it's effectively a $AJAX call. I'm sorry, this was like a little bit of a detour detailing what the algorithm was like 2 years ago. So you may be wondering what has changed since then. Now, the analyzer was significantly updated, so let me cover what the additions have been so far. We have added support for numerous values. So previously, it would not support storage of several different values for the same variable. This has been addressed. Why would we do that? Well, what you see here is an example of code where it comes in handy. If we are analyzing code, and in different branches, the variable gets different values assigned, the analyzer would simply have to store one, dropping the others. So what have we done in order to address this? Now, we have added a new type. This type, the value of which will contain an array of different values, or can at least do that. So when such code gets analyzed, the action variable will have a value set, and this set will actually contain two values, getSorted and list. Now let me tell you how it got implemented. Well, naturally we added a new type, so it will be supported by the analyzer. Also, in order for it to work, we need to update the semantics of various operations supported by the analyzer. Let me show some examples here. For instance, if we want to update the semantics of binary operations, so for the plus, for example, we'll be using value sets, and as a result, we'll have a set consisting of elements of the input sets. Or another one. So, for example, assignment of a field, and they're rather having a specific object, we're going to have a set of potential objects. Now, if such combinations are used, naturally, we will need to limit the size of these sets, because otherwise, they will get out of control too quickly. They will take up so much memory, and they will take forever to process. However, Georgy Alexandriev, in his report on the exponent, covered it very nicely. So naturally, we've introduced limits for the set sizes. Now, the second thing that has changed is that the analyzer now is building a better call graph. So it effectively develops a map where the key is the call site, and its values are a set of values that can be called in this particular spot. So such a map will contain records for every call site in the program. Once you find any call site as the analyzer is going around the AST tree, it will try to compute the value of Kali. If it succeeds, it will add to the map or to the call graph. It will add a separate record. Now let me show a specific example. Let's start with a simple one. So we have this variable f, and it has a function assigned to it. And then there is a function call. So as the analyzer reaches this point, it will try to calculate what's there in the place of the function being called. Like we said, the analyzer supports variables and also it supports functional values. That's why in its memory it will have a record like this, that for the function f there is a value because it returns ABC. So if we grab this particular value, or if it does that, it will be able to add to the call graph the following string. That function f effectively does this. It returns ABC. Now, let's imagine that we have several candidates here. So we have this conditional operator here, and then, different functions could be assigned to function f. So once analyzer gets to the call site, it will see what it has written down for variable f, and since we have different values possible for the value set, it will say that, okay, it's a set here. One of the elements of the set will return ABC, that will return 1, 2, 3, and then it will be able to add to the call graph the following record, that in line 9, calling function f will return one of the two strings effectively. And the third example I have here is with the object field. Like I said, the analyzer supports operations for assigning object fields and reading them, which means that here it will be able to determine that OB points to function return 1, 2, 3, and therefore it should be able to add a specific record to the call graph, which means that wherever the analyzer can calculate the value associated with a particular function, it should be able to add records to the call graph. Let's move on. Now, the next thing that got updated is the collection of arguments for all functions in the program. So for all the functions, we collect sets of potential values for the arguments, and then we develop a separate map. Now, value is effectively a set which contains potential values for argument 1, for argument 2, and so on and so forth. So how is it generated? Whenever we run into any function call, we try to calculate the arguments and, well, the value of the function as well, naturally. If we succeed in that, we should be able to add a record to the map. This means that for all the functions in the program, we now have a set of arguments that we can use. Now, the next thing we've updated is the way we deal with the values of functions returned, so to speak. Now, you might remember that we didn't have much in this respect. So none of the announced functions in the code had this provided for them. Now let's build a map for them. Now we build a map where the key is the function, where the function is the key, and the value returned is the set of potential values that such a function can return. Now, as we do code traversal, whenever we see return, we will calculate the value that it should actually return. And for the function that we are currently in and where this return is invoked, we add to the map a related record. It could be a new record where we can simply update an existing record. Now, this means that we have a set of returnable values for any function. So whenever we see, a function return, we can do better than unknown, which was the case before. Now, this is something already, right? But still not accurate enough, because with an algorithm like this, we will be mixing up all the values that any given function can return. Because you do remember that all the potential values are stored globally, but for different call sites, they will be mixed up. So confusion is very much possible. Now imagine that we have a function that does something with its argument and then returns a related argument. So for example, here, it simply adds a prefix. So, for two call sites, as I'm showing here in the slide, the return values will be mixed up. So, for both login URL and register URL, there will be two potential values possible. So, we decided to address this issue. And we have developed the following improvement. Now, when a function call is being processed, the analyzer will go to the function sort of emulating the call. So it will analyze the body of the function with the arguments having been calculated already. And then it will be able to ascertain the value returned. However, it won't really go too deep. Well, currently the depth is only 2, which means we can only go 2 calls down. And if you need to go to, say, level 3, the analyzer won't really do that. Instead, the value to be returned will simply come from the global table of all values available to the function. Now, such a limitation is easy to understand. Otherwise, the whole thing would get too bulky. Now, the next improvement we've added is class support, particularly object-oriented code. Previously, we were pretty lousy with analyzing such code because the analyzer would not really understand what this means. So what have we done in this respect? A, we have added new special values to the analysis algo itself. And 2 types here. One is class object, which is effectively the class itself. And it contains the list of class methods. And another one is instance, which is effectively a class, instance. So it contains regular class fields with data usually. And the two are obviously related. So an instance will effectively know which class object it belongs to, and the other way around. In order for it all to work inside the analyzer, we also had to update some of the operations supported. So the new operator for class object will return the required instance, so to speak, and when a method is invoked by instance, the method will be searched or will be looked up in the respective class object. And when analyzer algorithm is traversing AST, the value of this will be resolved into respective instance. So how are we going to know if we are inside a class method? And how are we going to determine what these classes are? Actually, the answers here will depend on how classes are merged, so to speak. So let's start with the modern syntax for JavaScript. So we can use the keyword of class, and that would be trivial. So, for different classes, there would be some specialized syntax, and it's obviously easy to analyze. It's something you can easily see in the code. So it's naturally very easy for the analyzer to identify the class and identify the methods associated with it. However, such syntax is a relatively recent addition to JavaScript. So online, you can easily find lots of other cases where you would first need to create a function for the class, and then you would assign fields to this function prototype. So this is what we call like vanilla announcements. And it usually requires using fPrototype M. Now, f is obviously a function, where m is the name of the field assigned to the prototype. So if we say that a prototype field is being assigned to a function, then we can simply establish an object class for it. And when we see new called by this function, we will obviously return the instance associated with it. Now, the new syntax, let me put it like this. So the developer could have developed a new class using the new class, but then it was sort of reworked to be used in old browsers, because for some reason they didn't want to use the latest features of JavaScript. So such a transmogrified code is also possible to register with the specific signatures they're using. Same is true for the methods associated with them. Like I said, for every class, we will create a single instance, meaning that for every class there is one global instance, whichever the call sites were. And this is not accurate enough at times, because this way we are potentially mixing up instance information. So, for different allocations or for different new call sites, we will have now different instances. I won't go into additional detail now, given the time constraint, though. But with this improvement, we are able to significantly increase accuracy by, significantly reducing the mixing up, so to speak. Now, module support. We've added to the analyzer support for different modules. The JavaScript code on the client side is usually modular, which is also the case for the servers. Now, let me explain what it will look like in the browser. Several different options are available. What you see quite often now is that bundlers are used. I'd even say it's still the most popular option. A bundle is effectively modules bundled together. Like usually you have, there's a gigantic object or array, and the fields there are functions. So each module sits in a separate function. Now the analyzer currently supports identifying different bundles by their syntactic signatures. Now, VPAC is the most commonly used bundler, so obviously we support this one, several others as well. So such module functions, and including modules, exports, and require are kind of identified inside them. So obviously exports is used to export specific values to make them available to other modules. Now, for every module we have identified like this, we are going to create a unique exports object. So naturally, you gotta build another map. Absolutely. We will develop a map of modules which will map module IDs to their names. Now, inside bundles, they could be strings or figures. And the value will be exports. So this is something that require is going to return. Now, shown here are the operations supported by the analyzer. So when we are traversing AST, when this traversal is inside the module, experts and require should resolve into respective values. Now let's look at how the require function is going to work. It will look into our module map, and using the ID as a key, it will take from the map the experts that we need. Besides the bundles, we sometimes see native modules being used. So modern JavaScript code will support some keywords such as import and export, so we can import modules using native language properties without using the bundles, so to speak. So it's easier to support such modules. So this whole system with exports and imports and keywords, it was designed in the way to make it easier for us to analyze such code, to see what's importing and exporting and what's being imported and exported.
Вот. Ну и сейчас еще не все далеко перешли на нативные модули, но мы...
native modules are still not used everywhere, but over time, naturally, more and more websites are moving from bundled code to native modules requiring this new syntax, which means that with the support of this feature, we are sort of increasing our coverage. Another feature we've added is library matching by value. Like I mentioned, if a library object has been renamed or a library function has had a different variable assigned to it, probably with a different name, such calls previously would not be recognized because the analyzer was matching AJAX calls by names. And in order to address this, we have introduced libObject and libfunction. So libObject is responsible for the library object, while libfunction obviously is responsible for the function. So we are creating this predetermined objects for predetermined names. For example, we'll know that global objects with names like this will be responsible for libraries, and for the library functions that we have been able to match using their AST signatures. So as we process calls, we are going to look at names. This is something we are still going to continue, but we'll also be interested in computing the values of the functions being called. And if they prove to be lib functions, we will know that this is effectively an AJAX call.
And finally, I would like to say about some simple things about some. For example, we added AJAX support, the place where we send the request to the server. It looks like this. We use the window.open function, and we also work with document location. By the way, document location is not just a function call. We use equal sign. I'm not just talking about document location, I'm talking about any assignment signs like window location, .rev, and so on. And previously I mentioned that we were working with the call function that sends a request to the server, and I think it would be more correct to say that we are looking for request to the interface that send requests to the server from the script. And oftentimes they look like function calls, but not always, because if we work with the location, it will also send a request, right? But we need to add these to the analysis, and it was quite simple. It's just a support of another STL bus where we want to calculate the argument. But it was actually quite quite profitable, what I mean to say. So compare what was before to what we have now. Now the analyzer supports bundled code, and the code which is uses here different classes and methods that read this or write this. And these are examples. Here you can see on the screen. If we send the request to the server, they will be able to find this. Next, I've already covered something where we improved our analysis or analyzer. What were the results? We wanted to understand if it became better, and if it became better, can we measure this, to measure the quality somehow? And to do so, we wanted to have a marked data set where we know what kind of results it should give. When we give results, we wanted to go through with our analyzer and calculate the score. But we did not have this kind of data set, so we had to create our own. And we've created our own data set that has pages. Pages, I mean HTML files and resources which are used on these HTML files and pages. And manually, they were marked on potential requests. This dataset contains pages. Some of them are random pages from the internet, from Ajax website list, and some of them from the websites which were used in bug bounty programs. And besides the scripts, obviously they had scripts, they were able to run the analyzer and calculate the score. You can use this as a benchmark for any tool that mines web pages for requests, and we decided to publish it. Here you can see the link to GitHub, and it will be available at the end of the presentation. So what do we get as a result? Using this dataset, what kind of metrics do we get at the end? We can see that the main metrics is average coverage, all these found endpoints. And obviously, we calculated for each of the pages what kind of endpoints should be found and what did we find. And then we make an average for the whole dataset. Here we can see that the coverage was 26.5 and became 38.6%, basically 12% increase for the coverage. And the average time for analysis, last time I was asked about analysis time, I did not give an accurate answer that time, and that's why I wanted to give you an accurate answer this time. Previously it was about 49 seconds, and now 2 minutes and 50 seconds. Here we can see that all those beautification, they actually cost us time. But still we improved our coverage, and 2 minutes and 50 seconds is not too bad. Obviously it's not great, but it's not too bad. Besides our dataset, we've decided to compare with other tools for the already existing applications which were created by someone else. And I think it will be an honest comparison. But besides that, this is what science requires us to do. If we want to publish in articles, talk about it in conferences, we have to compare with the data and other tools which are known in the literature and which were used as benchmarks before. So here we had an experiment and we compared it with other 6 tools on 5 applications you can see here on the screen. So what do we get as a result? As a result, we have this table. What can we see here? On 2 applications, we demonstrated worse results on WebGot and Weavit. It's easier to use with dynamic analysis on those applications, and with crawling, with an attempt to send the request, it's easier to see those requests. In 2 applications, we demonstrated better results, and in one, we had an equal result with DVWA. And for this tent, where we had an equal result, it actually was quite simple, where it's easy to find all the endpoints, so it's no surprise that we had the same results. How did we manage to get better results? Let's delve into it. Let's start with JShop. It's a famous test application that contains vulnerabilities for test scanners. Obviously, you can do this manually using this JShop, and it's basically a single-page application. And you have a single page, and it contains all or almost all client code, and all the other pages in terms of user are basically the same pages where JavaScript rewrites the markdown, and then you use JSON file just to get access to them and send requests. And our analyzer was able to analyze this code on this page And since they have basically the whole client code, they were able to find all the requests for APIs, including those that are beyond authentication, even those they are complex, so you don't really know how to trigger them from the interface. And actually, one of these handles refers and asks endpoint to download files, and this endpoint is invisible in the interface if you do not pass the authentication process. But it receives requests without authentication. You can see them in the client code. And if you refer to it, if you basically knock at its door, you can explore and use the vulnerability. You can send the explorer, and it will be exit E, I think, and then you will be able to find the vulnerability there without any credentials for this application, by just looking this handle in client.js using statistical analysis. Next point was MyBB. It's a forum engine. And in the setting where it's used in other articles and other experiments and where we used it, this engine is basically installed, and then it does not have any additional settings. It does not have any forums, no posts, no comments. And in this pure sense, in this pure form, it's analyzed by different sensors and crawlers and stuff. It's not SPA, it's an old school application, but since it does not have any posts, it does not have any comments, many handles cannot be triggered dynamically. If you do not have comments, if you do not have posts, you cannot comment them. If you do not have comments, you cannot like them. Still, the JavaScript has all those requests. So if you can see them, you can detect them, you can try to get to them, and maybe potentially exploit vulnerability. And the situation where we have some kind of application in the network where it's deployed, but it does not have all the necessary settings, it does not work with the data, I think it's quite plausible what might happen at the client side. They already have the main web page, the website, it works, it's operational, but other applications might be deployed but without any additional settings, and they might have vulnerabilities. Okay, all that was regarding the tests on synthetical experiments, but what about the real vulnerabilities? We've performed quite a lot of experiments during the past time, and I don't really have much time left, so that's why I'll focus on a few of them, all of them from Bug Bounty, and all of them during the last 90 days. The first example is basically a standard case. We have some kind of script.js script, and with function change org details. Obviously, we change the URLs and all the details. It's not real for all the parameters, it's just for the sake of the example. Here we have an internet store, and the endpoint that changes the organization details usually has some kind of privileges. It's not just a normal user, just normal buyer. Still, we can see that endpoint in the client JavaScript, and probably it's shared by multiple pages, if it's called common. We do not see any function calls. It is inside the code, but we do not know where it's called. Or on the pages where we can see it's not called, but we can see this request if we just analyze the code, read the code, and you can see it here on the screen, and that's why we're able to locate it. Next, we used 4 different bug bounty programs, and we found XSS requests or inquiries through window open and document location, where we were assigning something to document location. So how does this happen? Why were we able to locate them, and why nobody did this before us? Why this vulnerability still exists? The first case is like this. We use window open to open a window, a pop-up window that uses authentication to process. Here you can see with the code, so there is a condition if authentication 2 is used, authentication 2.0 is used, then this window will pop up. But in reality, this authentication auth 2.0 was turned off. But the handle, it still exists on the server, and the server replies to the requests, even if the auth 2.0 is not working on the page. Another example with another internet store, and they have search and they use document location. It looks like a search query, where this query additionally processed, and we cannot send the query itself. Instead, we get a list of potential options. Maybe you saw this when you, in Yandex Map or Yandex Taxi, you try to enter a location, and then you have a pop-up window from proposed potential addresses or maybe items where you want to go, what you want to buy. You couldn't just look for them, you had to select from very specific examples from that list, and then it would look for it. And this kind of case for manual pen testing is very simple. Obviously, pen tests will see this pop-up window, they will select something, and it will send the request. But for automatic pen testing, this might be quite problematic. The crawler would have to wait for the list to come up, would have to understand that it has to click somewhere between among these options, not somewhere else, otherwise the list will go off. So when we worked with this example, it was easier to go through with statistical analysis, and we also had XSS in this case. And example number 3, we have an application, and that application has a client code that sends requests for this handle API search customers. The function that sends requests, it does not code anywhere, and the data that returned by this handle are returned without any authentication. We just send in the body of email user, and we get the whole information regarding the user on this website without any authentication. And basically it's data leak, quite serious. But at the same time, this is the case for manual analysis, as opposed to the previous example, because scanners would have problems to understand if something goes wrong. There is no XSS in this handle, no problems, but this data were not supposed to be given to us without authentication. But this kind of vulnerability for modern scanners is a very problematic thing. But a real pen tester, a real analyst would see this kind of URL, this kind of request in the list. He would or she would think, well, that's an interesting handle, should it work without authentication? And probably they were able to locate this vulnerability. And by the way, when during the previous presentation, I thought that I was asked maybe all those requests could be found in traffic. Maybe there's access to WAF traffic, and not always we have access to traffic. But this kind of experiment, we also had this kind of experiment. We have an ability to integrate with our WAF or our scanner, and they can take endpoints from the traffic. And the case where the client code would have a function which is not called anywhere. We also had this in one of our experiments for one of our clients. The function was not called in the client code, and it was never called. Users do not use this function, and that's why there was no traffic. Even though the request works and the server responds, there is client code, but it's dead, and because it's dead, we did not have any transaction using WAF. Another point which was asked during the previous presentation, my previous presentation, was that are we ready to share our source code for our analyzer? And I'm talking about our analyzer for the second year, but you are probably listening and waiting, can we actually use your analyzer in our life? Well, the question is actually quite complicated. We thought a little bit and discussed it a little bit, and we decided, yes. We decided that we will launch a community version of our analyzer, and it will be publicly accessible. So what does it have? This is a publicly accessible API that allows to run an analyzer on a specific page or API or JSON file. You can use this URL. The interface should be operationable. Besides this being an API, it has an interface that allows you to run it manually and test it manually. Currently, this This is just a handle you can see in the interface, but in reality, we will have registration and authentication, but we will do it later. And currently, we are starting to publish the source code of our analyzer. We've already published part of it. It would not be very interesting. So almost all the features which we covered during the previous presentations and the majority which I covered now, they are already uploaded. They are there online, publicly available. You can go there, you can check it out, you can try it yourself. And we also we plan to have a bigger update with uploading a big part of this code somewhere at the end of April. We decided to call it Real Arc. And do you know what does it mean, Real Arc? By show of hands, yes. Somebody wants to guess what it means. Okay. They do not have a microphone, so maybe they do.
Да, Дань, это кроулер наоборот, да?
I think it's reverse crawler. Yes, it's the word crawler, but it's reversed. And why do you think it's reversed? What's your guess?
Ну блин, вы же статику делаете, не динамик.
Well, you work with static, you don't work with dynamic, you work in static. Yes, it is true, you are correct. Crawlers, how do they look for potential problems? They interact with interface, they click, they scroll. We instead go the other direction. We use a completely different approach. Our analyzer doesn't do anything with the page. It just uploads it using URL and then has no interaction with the page. And this is what I wanted to cover during this presentation. I would like to ask you to try this analyzer. Maybe it will demonstrate, maybe it will give you some kind of endpoint you didn't see before, and especially if you don't have enough time to go through the whole JSON code which is present on a web page. Those URLs will be at the end of the presentation. And if you are interested in JavaScript analysis about our analyzer, then you can check out our Moscow State University blog. We write about this analyzer. We publish multiple posts and articles, pictures. Somebody prefers to read instead of listening. And you can subscribe and we will publish more. And this is all. I would like to thank you for your attention. Here is the link for the presentation that has everything that I mentioned before. And that's all. I was asked to add this QR code where you can leave your review and mark our presentation if it was good or if it was bad. Thank you, Daniil. I would like to ask you a few questions that we got from our audience. Did you try to turn off the limitations for value set limitations? And if you do, what kind of results did you get? I think that's a great question. Obviously, we tried, so what kind of results did we get? Well, actually, it critically affects both performance and memory consumption. And working with these combinations of different sets can be very, very painful. Maybe we wouldn't run out of memory. It's not like we'll have billions of elements and they will go beyond RAM. No. While calculating the combination of big sets and some operations with them, the analyzer would be very, very slow. Maybe it will be addition, maybe it will be working with a string, but still it will be very, very slow. And that's why we decided to decrease this limit. Previously it was about 100, then we decreased it to 32, I think. But you can see it on the code, it's available. Do you calculate the variance for arrays, dictionaries, and so on? And if you do, how do you do that? Yes, we do. We perform calculations. There is a function in the code. So the question is about the complex structure in the code. Not just set of strings or numbers, but about the structure that contains potential elements that might be sets or subsets. Some of those sets might be subsets of other sets and so on. Yes, this is about the exponent, and it's true. Those combinations are calculated, and the analyzer has a function that's called produce combinations, that basically produces combinations, and it goes through all of them with recursion, goes through everything that's inside the sets, and builds potential variants and options of that, and as a result we get the complete picture of them. I'm not sure if I should waste time explaining how it works, but it's a recursive function, it's present in the code, you can check it out. Thank you. Do you calculate the endpoints and the argument values for the function that are passed through DI or some kind of framework like AngularJS? I think this is a good question. See, what analyzer is trying to do? Well, it tries to do that, but it's very hard for it to analyze complex libraries, even jQuery. So when we were developing this, we try not to disallow this. Where we need to cover it, we use special handling within the analyzer. For example, in jQuery, the analyzer will not get inside. It will have a break, and it will not just get inside this jQuery. So the answer is, for AngularJS, it will try to do so, but probably it will not be able to do like honest analysis. But where we needed this to increase the coverage, we used special handling. Thank you. Did new features slow down your performance? And how it works with branching and recursion? So once again, how hard was the slowdown of the performance because of the new features? I think this is also a good question. New features of our JavaScript usually do not slow it down, but increase the speed instead, because these features have more expressive power, and you do not need to create a complicated code that would do the same. For example, fetching is easier, import is easier compared to the require function in the bundler, which is very hard to analyze. But that being said, the other part, if I'm not talking about the language features, but about the modern applications, then yes, modern applications have megabytes and megabytes of code and can be quite heavy. Currently, we are able to stay within some reasonable limits in terms of resource and analysis consumption, and basically any page we will take will be analyzed by analyzer in this or that way. But the majority of the code are actually complicated, and they are quite troublesome, and they were not created by developers themselves. They have libraries, and obviously those libraries are not analyzed by the analyzer, and sometimes we have to wait for minutes for the analyzer to continue its work. Are all these scripts analyzed at the same time, or do you merge the resources? And if you merge, do you have any conflicts? I think this is also a good question. We do merge them. All the scripts are analyzed in their entirety altogether, and to avoid conflicts, if somewhere language was supposed to be used, we isolate them. If we had only two scripts and they had some kind of variable that had the same name, then one of them would rewrite the other, but the same would happen for the real analysis of JavaScript. So we do not really break anything that was before. It's reasonable, but if it's a script typer using a module, use a JS model, then they have isolated scope, and we isolate it in order to have the same name of the functions or variables, so that there will be no clash between them. Do you have full positives for your analyzer when it reports endpoints which do not exist? Yes, they have full positives. Can your analyzer distinguish parameterized endpoints, work with templates, their parameters, and their potential values? I really like this question. So this is not a trivial task, because if you just look at the request, we cannot say which part of it is parametric and which part is fixed and defines the request. So if we change that, then the server would not process it or would believe this is from a different handle. So what can we do? Well, we can work in the best effort mode because we have client code. And to answer this, we need server code with server router and where we can see specific requests and how they are processed. So what can we do? If we can see that some part has arrived from a user and it was not defined during the analysis, for example, they do not have any input value, somebody got some information from an input tree, then we believe that this was parametric. If some values were inside the code, then we will try to return options for all of those values which we're able to find. But in the end, obviously, we cannot say for sure if those were parameters or a fixed part. But if we're unable to see if it was values, if we do not know where it get from, we assume that it was the variable part. Can the calculation of the variables result in a DDoS attack? Well, you mean DDoS attack at the analyzer? Probably yes. I think there are two potential interpretations of this question. If we DDoS the server because we might have many requests, or maybe the analyzer itself is DDoSed. Well, for the analyzer, there is a limit for sets. It was not the only limit. They have multiple limits, and we tried to set those limits so that an analyzer would not be DDoSed. It would not just run out of memory. If we are in the situation where an analyzer is broken down, for example, it consumes too much memory, we try to fix it, we try to think what should be improved, and not to lose the coverage, but also to improve the situation, and obviously we fix these limits if it's needed. In the current version, it should not happen, but obviously in theory there could be a bug, and we try to fix the situations beforehand. And regarding the server, the analyzer does not send requests to the server itself. Oh, what I mean is that the one they found, they just pass them to the scanner or the user. If they have too many options for requests, then yes, it should not be just sent blindly. It should be done by scanner or by user. They should think maybe there are too many requests so that to avoid DDoSing the server, analyzer do not send requests so they cannot DDoS the server. And final question, do you plan to use KFG for your analysis? Some very good questions, actually. This is a very good question. It's very interesting to try myself. I would like to implement this kind of version that uses it and see how it operates, how it works. I think it will be very interesting to see how it plays out. On the other hand, we do understand that this kind of analysis would be a little bit heavier. So I think this is an interesting area for potential research, but how and when and if it will be planned, I think this is a different matter. I don't really know myself, but I think this is an interesting area.